Hi, I'm Mark Wilson, the engineering heretic, and today I wanted to have another discussion. The other one was relatively popular and on the internet, and I thought I'd discuss a few more issues when it comes to tool making. Now, I mentioned in my previous video that a lot of tool makers had swung in this particular part of the world in Australia had swung over to precision machining, and that's true. And I talked about the stresses on tool making and how the collapse of the car industry and the collapse of the tool making industry happened. But now I want to discuss tool making itself and why it's important, what it means, and what exactly is a tool maker, and how is that different than a precision machinist. Well, let's talk about a precision machinist first, because that's where some tool makers have morphed into. Precision machining is usually the people who do this type of work. They're usually working on machine tools. We're talking about CNC machines, and usually fairly high-end ones with spindles that run at a very high rate and can move very quickly. And we're talking about high precision bearings and all sorts of things to do precision machining. We're talking mostly milling machines. They're the sorts of things that CNC mills and things like that. The sort of things capable of making turbine blades and things like that for the aircraft industry, and also for other blades for power generating plants and steam turbines and things like that. The precision machining related to those is usually on 4-axis, sometimes even 5-axis machines, cutting very complicated shapes. They're usually developed, the cut parts are usually developed by, they're on CAD, of course, and then that's translated over into CAM, and then machined to a very high precise rate on different components. Aircraft components, precision components, or components for anything around the world. Now, these things here are made to CAD data. Quite often they're made to high precision, and they're made to the specifications of the designer. And that is precision machining, and we're working often to drawings with tolerances that really have no leeway for any interpretation. They're just machined to the size within the tolerance. It's acceptable or it's not. It's maybe reworked. So a precision machinist is a person who works in that field. They often run CAM generated usually from an office somewhere for the more complicated things. And then there's the field of just shop floor programming and just straight code programming for quite simple things. The 2D, 2.5D type of machining. And of course, a machinist will, that's what they're responsible for, the running of these machines, the setting up, establishing the reference positions, monitoring the machine, maintaining the tooling, and then rudimentary checking themselves to drawings, gauges and things like that, possibly even just precision measuring themselves. And of course then it would go on to some sort of lab. They'd be inspected on a CMM machine. So how is that different than tool making? Tool makers are a variation. Just to make a bit of a comment, when I was doing my apprenticeship, the place where I did my apprenticeship was called Paran Die Services, and the guy who owned the place was Fred Sands, and he made a comment to me very early on in the trade. He says, never be a tool maker for tool making's sake. And that is a very fair comment for a tool maker. Tool makers don't necessarily work to precision drawings. If their hand is something they make, like a part for an injection mold or even an injection mold completely, they will look at the component drawing, and if they're designing or building, let's say a core pin or something like that, The core pin hole maybe have it may be let's a larger side. Maybe the core pin hole size it comes out of the mold with a hole in it. There's a pin that does that in the mold. A toolmaker will make a core pin with no drawings, basically, or a sketch that they've made based on the build-up of the mold itself, and they will work out the full length of things. They will then have a look at the drawing. They will more than likely put on the shrinkage rate of the components. So if it was a shrinkage rate of, say, 0.6%, they would add that to the sizes of the core pin hole. And the core pin hole size would also have a tolerance. Let's say the tolerance is going to be 10 to 10.5. That would be the tolerance. So that hole could be any of the finished product could be that. A toolmaker, if they were building that particular part, would work out the length, make up a sketch. They would get on the lathe. They would find some soft, what we call core pin. Usually in a material called H13, which is the general one they use for those types of things, which is a hot die steel. They would then machine down. They would allow the shrinkage, so the 10 would be, let's say, to be up to maybe 0.1 larger than that. Toolmaker would make the core pin size to 0.1 larger, so 10.1, but with 10.06, and of course, and you think, oh well, that's all well and good. But an injection mold requires a thing called draft, and sometimes on the drawing it just says a standard draft is 1 degree or whatever, or a half degree. But on a plastic part, there is a thing called draft, which is a taper that allows any sort of moulding to come out of the mould, starting off a little bit tight to start with, but get easier as the part lifts out. Now, a toolmaker, if they get a drawing like that, they will reinterpret the drawing to suit the draft. So what they will do is they would make the bottom size of that core pin 10.6, and the top of over its length, they would make that 10.1. So they taper, they build the tolerance into the taper of the pin. Because most of the time in injection moulding, you get this comment, draft within tolerance. In other words, ignore the standard tolerance of maybe a 1 degree, ignore that, and put this taper on built within the tolerance. So when the part is moulded, of course, you go to measure that. You measure one side, it's the top tolerance, and the other end, it's the bottom tolerance, and the draft is built into that. Not only will a toolmaker do that, the toolmaker will also add a little bit more. And there's a thing called maximum metal condition, where you would add probably just a little bit more, because you'd be a little bit concerned if this shrunk too much, you'd end up undersized. So you'd actually deliberately make the thing a little bit larger than that. Probably another 10% on the tolerance you would add to that. And then, of course, you would polish this part. If you're on a lathe, well, you can polish it pretty well, but you need to have a reasonably good polish for anything to come out of a mould. And of course, a toolmaker would build this into the part they're making. So from a component drawing and just basically a build-up of the mould they're making, a toolmaker will work all this out and build this into what they're doing. Now, you end up with a part from mould, and that's all well and good. So next time, if you need to replace that, generally on an injection mould, something that big and everything, it's going to last many, many years, particularly in plastic injection moulding. It's different in die casting. You tend to get about 100,000 shots out of something, and you're rebuilding the mould, sometimes just the inserts itself. The zinc, that's the zinc pressure die casting. The aluminium die casting is about half of that again, maybe 50,000 shots, and you're rebuilding it again. But we'll stick with plastics because it's a bit easier, and I like that better anyway. Now, that leads me to the next thing about tool making. A tool maker will be so concerned, like in an injection mold, there is a top half and a bottom half. When they close flat on, that's all fine. The plastic is not going to squirt out the gaps because it's just basically one flat sheet, one flat block on top of another. Usually precision ground. They're what we call the shut face or the shut off or the parting line, or whatever you want to call it, is that. On the sides of things where things become steeper, then when you're cutting things like that, you get a little, because when you're fitting that way, you're closing up the mold. It doesn't really matter. The actual end up height is not critical in mold. The machine will close up, and it doesn't really matter if the whole mold height is a half a mil higher or lower than what it's supposed to be on the drawing. It doesn't really matter. On the sides of things, when things come down near vertical, you end up with a near vertical shut face. So you're something that's on an angle. Okay. The tolerance on these things here, because plastic will ooze out in the wrong spot, called a flash, will squirt across in these areas and cause these things called flashes and things like that. You may see them on some of the some very cheap molded parts. You look at things and you'll see little bits of plastic sticking off where they're not supposed to be. That's a flash. It may be because of wear on the mould, it may be because there was a fault on the mould or something like that. But generally in Australia, we try and make sure we build a mould that doesn't require removal of these flashes to any great degree. In near vertical, what we call shut-offs or part lines, this becomes really critical. And because plastic will flash in around about 0.05 of a millimetre, anything more than that, which is the old scale, that 2 thou. Much more than that, plastic will start squirting out. Not a long way, but leave these little whiskers on things. And if you're building a mould and you're closing a mould with a very, very high, and it's quite often you do have these quite high angles there, you'll be concerned that if you machine something undersized, you'll create a gap and there's no way of fixing it. The height's fine because that just closes up the machine more. The width on shut-off faces is really important. And a toolmaker will actually build into what they're doing and allow for just a little bit of fitting. In other words, they're going to make the part with stock on, fit the component together, bring the mould down with a thing called bearing blue, which they call high spot blue, and touch it on there, lift it up, and see where this interference is, and remove just by hand with usually a pencil grinder, sometimes hand work and things like that, to allow this mold to close further and further. And generally when you start on some of these really complicated shapes, you end up like a 3 mil gap or something like that before the mold closes. And it does take some time, and you'll have it in a press or even on the bench. You will blue up one side of it, close it, lift it away, and on the other side there you'll see it printing off on the other side, and a toolmaker will just with a pencil grinder take off those edges and what have you, of those high spots, and then they'll clean it up again, close it again, re-blue the other half, and just the bits that were rubbed off last time. And keep doing this process until such time as they close the mould. So every part on an injection mould is hand fitted, done by toolmakers. Now this is pretty much a moulding thing. It's not usually a press tool thing. That's a little bit of a different realm. It still is tool making, but I'm a plastic mould person. So a toolmaker will make things with metal on, get them heat treated, they'll warp a bit in that, and they'll be so concerned about going undersized. In other words, if that gap ends up on the mould down here and they close off and there's a gap there, you'll either be welding or making the part again. So to avoid that, they leave stock on and then they hand fit until such time as the mould is closed. So the top half and the bottom half of a mould are bespoke. They're made to suit things. The product it produces, the mouldings, they're subject to strict checking and what have you, particularly in engineering components. Not so much in like the toy industry and things like that. They're pretty wide tolerances, but they're still worried about flash on things. but each and every component that's made in a mould, they can be made completely on a CNC machine. They're often not. They'll be machined up. They'll need to have heat treatment done. They'll need to be surface ground to get these accurate faces correct. They will only be, like I said with Francois, only be a toolmaker when it's important. Never be a toolmaker for toolmaking's sake. So you will allow and make things, and that is the difference between a toolmaker and a machinist. Not only that, a machinist will be working on a CNC machine and they will be quite specialised in what they do. A toolmaker is generally can generally do run many machines, including CNC. Back in the 70s, when I did my apprenticeship, it was the inserts and what have you in die blocks were finished machined by using a pantograph process from patterns made. That's not the case these days. We have CAD models and we machine to the CAD models directly. It's a much quicker process and it's way more efficient and way more precision. But it still requires a toolmaker to do that. Not only is that, there's simple things that need to be made up on molds, like rails and sliding things and all sorts of stuff. They'll be made up and the toolmaker will then assemble this, adjust and tweak things to make sure things slide around the right spot. They will fit them all together and until the whole thing works. And also they will end up, so quite often you'll put things together, you'll have a hole drilled on an angle through a number of components. It's just as easy to put the whole thing together, put it up in a radial drill and drill the hole through every part in the one action, then pull it all apart and adjust a few things. You could have a CAD model for everything, but then that would leave a CNC machine to machine every component to the precision size. Now, that is not really, there's no need for that. Toolmaking relies on the skill of a toolmaker to build things together, to make things, adjust things, and by the time it's finished, each and every component will be made particularly for that mold. They're not interchangeable parts. And that's what a toolmaker does. They work with these things. They work with slight warpages in heat treatment. They allow for fitment. They allow for tweaks on drawings. They'll allow for things like that. That's a toolmaker, and that is what they do. And of course, if you move from toolmaking to precision machining, then you're looking at drawings and CAD models that are just, there's no question about what they're supposed to be. And they are talking about making interchangeable parts. So you make a part for a jet engine, the next part should be within tolerance and should fit directly in it. And the next part you make, and so on. In toolmaking, that is not the case. A toolmaker tweaks and adjusts and works things so they fit, and they're making bespoke components. And that's essentially what a toolmaker does. They use a lot of machines, they have a lot of skills, and they're encouraged to think on their own, to problem solve, whereas a machinist is working to a format that is somewhat fixed. They may well develop better holding methods and things like that. They may make their own jigs and things like that. Quite often, a toolmaker will make a jig for a precision machinist to machine, or the toolmaker is the precision machinist. But that's the difference between toolmaking and precision machining. And I'm Mark Wilson, and thanks for watching.